quantum support vector machine is giving 84%, and you have observed it is running more than 30 seconds. And similarly, you have observed a classical support vector machine ran for less than 1 second. So with this presentation or demonstration, I open to the floor for Q&A. You ask the question, I will answer. Then I will build the next quantum machine learning, and I will explain how quantum machine learning is achieved, how it is working both mathematically as well as from the application point of view. Any question? Please type the question in chat window. Based on your question, I will answer.
Few of the participants have joined late, I guess. Now there are 70 participants.
Okay.
Is it possible for you to just tell like 5 minutes before? Can you just explain once again? I am getting a few messages in my phone.
Oh, okay. See, actually,
Otherwise, they will not be able to follow it.
I understand, madam. I ready to go back to basics and then come back.
A lot of message in that WhatsApp.
I know, I
Yes,
know.
sir.
Yeah. So
Just
we will go with.
yes, sir.
I know, madam, because it is a new concept. There may be yeah, the difference between the knowledge level of few individuals and then few other individuals will be very high. That is the reason why I started with the basic question.
Yes.
I will go with the basics, and some of the members joined late, and most of them may not be very confident about the basics. So I will go with basics. Then I will demonstrate this one, because when you see the code, you will realize that code is very simple. But how it is doing the quantum operation? Only 4 objects: Z feature map, sampler, compute and compute, fidelity, quantum kernel. But it is very difficult even for the advanced level faculties. Okay, right. Now let me set up the I will go back and then explain the foundational concept, then come back. So for those who joined late, we started with a high level explanation to what is superposition with an example of spin of electron and photon of electron, polarity of photon, and I explained with this example. A mathematical representation psi ket equals to alpha 0 petrels beta 1 ket. That is what we started. Then I did not explain entanglement. Then straight away jumped into demonstration of quantum machine learning. Before that, I gave a short explanation to machine learning, classical machine learning, and even I did not talk about anything. My assumption is that most of us knows classical machine learning. I'm keeping this for a reference only. Later, this PPT will be shared with you, so you can go through that one. Then I talked about what how quantum machine learning falls under the intersection of machine learning, quantum computing, and then optimization. And it is also called the next big thing because it became a horizontal capability for other quantum computing verticals like optimization, biotechnology, chemistry, simulation, any other quantum build solutions. They depending on a quantum machine learning as the foundational or one of the horizontal capability. That is the reason why quantum machine learning is considered as the next big thing. Then I walk through some of the mathematical foundation for classical machine learning. Then that same mathematical explanation, mathematical models explained with application. Then real life use cases for machine learning. Why it is applicable to quantum machine learning also. Then I started with this Venn diagram. Then the benefits. After that, I jumped to the demonstration. Now I'm going to explain the program. We have a simple support vector machine based on iris dataset. I strongly believe that most of us or all of us know what is iris dataset. So I did not explain what is iris dataset straight away. I showed this program which is importing the necessary libraries, and we are reading that. Then we are building a classical support vector machine using, my God, sorry, using sklearn based support vector classifier. And that output, when I execute, you observed that it is giving 100% accuracy, and it ran very fast, executed very fast. Then we have a program, a quantum support vector machine, which needs four components: a data encoding and a QPU access, then a fidelity, then kernel. This kernel is composed with the help of fidelity and the feature map, which is the data encoding component. Then these things are passed to a sampler, the fidelity, using the sampler, which is the QPU interface. And those things are passed as an argument to quantum support vector classifier, which is imported from Qiskit machine learning. And here only we are doing the fit operation and predict operation. Then when we predicted the sampled unseen new data as a typical classical machine learning. And what we observed, a quantum support vector machine is giving 84%, and it took more than 30 seconds compared to classical support vector machine. This is what we have completed so far. Now I will share this program in your chat window. Those who are all joined with the laptop, feel free to, yeah, I'm going to explain the circuit now. Feel free to run the program. Oh, I cannot share the program. How can I try to paste the program here? Is this? Ah, okay, right. Let me simply drag and drop. Madam, it looks like I cannot share. Madam, shall I share to your WhatsApp? Can you share it with others?
Yes, sir. Sure, sir.
Okay, madam.
Yes,
I'm
sir.
sending to your
I'll
WhatsApp.
post in the. Yes, sir.
Just a few seconds, I will share with you.
Yes, sir. Please take your time, sir. Yeah.
Done, madam. Yeah, I shared, madam. You can share with all members. Now I'm going to explain the circuit. Let me share my screen again. Hope you are seeing my screen now. Okay. So now the circuit, what you are seeing here, it has some Hadamard gate, some P rotation, and some entanglements. That's it. But how it is performing the support vector classification? So let me explain this in my PPT. Hmm. You are seeing four components, right? In a solution, you are seeing four components. One is feature map. Other one is QPU sampler, which is sampler. Then fidelity. The fourth one is kernel. So the feature map is serving the purpose of data encoding and it is using the method called angle encoding. It's using phase encoding or angle encoding. Okay, so these are the foundational concepts. Now I will explain what is this feature map is about. Can I go or you have any other question? I will stop here, wait for your question in the chat window. Okay, there is a question. Explain the difference in stages where we are using ML and QML. Yeah. So ML, it is somewhat matured approach. And as of now, the machine learning almost it is applied all domain because of its capability to classify and based on the classification we can build prediction, recommendation, prescription, all those things. So that is somewhat matured approach, whereas quantum machine learning still it's a nascent stage and we are not seeing a good performance or accuracy compared to their classical counterpart. So as of now the industry is building proof of concept and prototyping only. That is the current stage of quantum machine learning. But what I'm seeing, see, when I started working on the quantum machine learning in 2017, there are only 4 models: quantum support vector machine, quantum neural network, and quantum convolution neural network as a quantum data classical model. Even quantum model was not available at the time. But now, after 8 years, what we are seeing now, we have lot of quantum machine learning models. I will type here because that will give you a clear picture. Quantum support vector machine, quantum neural network, quantum convolution neural network, quantum transfer learning, and quantum LSTM, quantum reservoir computing, and quantum physics informed neural network. There are few more things are there. QGAN, yeah, QGAN is also there. So these models are available as of 2025. Madam, is that what you want to know, or any other question or follow-up question?
For feature mapping, can we use the bioalgorithms?
Like nature-inspired algorithms?
Yeah, that's right.
See, nature-inspired algorithms, which falls under meta-heuristics, they fall under what is called quantum-inspired approach.
Feature selection.
Quantum-inspired
approach. Feature selection we apply in classical ML. For
like
QML,
PCA,
what we are doing,
yeah, like PCA or any evolutionary algorithm or genetic algorithm. These things are all used in the classical. So when it comes to quantum, you can have the quantum principal component analysis. That is also available. QPCA also available. You can use that one also. Or you can go for quantum inspired, I will write it here, quantum inspired genetic algorithm or evolutionary algorithm. There are set of quantum inspired evolutionary algorithm, right? QIGA, sorry, QIGA, quantum inspired genetic algorithm, QIEA, quantum inspired evolutionary algorithm, QIPSO, quantum inspired particle swarm optimization. These are the 3 algorithms, at least in my knowledge, being explored by industry. There may be new inspired algorithm may come under nature inspired or evolution algorithm, but as of now these 3 things are somewhat popular. Hope that answered your question, sir.
Yes, sir. Definitely.
Thank you, sir. So now,
Apart from classification, is there any regression type of models?
yes, sir, quantum support vector regressor is also available under quantum machine learning library. I am going to show that quantum machine learning documentation. There I will show you. Before that, I'm checking some question. Sujitra madam asked, quantum sequential neural network. Can you brief of it? Yes, madam. I will explain quantum neural network. It's a separate section because that is very important part of our session. Before that, I will answer. Sorry, Doctor, I did not get your name. I will explain.
Kumar,
Dr. Kumar, I will explain your question to your answer to your question. So the important point is getting help from IBM quantum Qiskit ecosystem. You have to search for Qiskit ecosystem. This is very important point because give me a second. I have to connect my charger. Let me stop my camera. 1 minute. There. Sorry about it. So search for Qiskit ecosystem. That Qiskit ecosystem will open a separate uh, subsite in your IBM Qiskit. I will share this URL in the chat window because in my observation and experience with multiple sessions, most of us don't know this URL, but very few knows who are actively working on this one. Here you can see almost many new quantum packages. Go to this Qiskit machine learning documentation. Here you will see all APIs offered by Qiskit for quantum machine learning. Obviously, see, tutorial is what I recommend. Go through each tutorial, you will understand all those things very clearly. Sir, if you see here neural network classifier and regressor, but I'm going to show from the API reference. Under API reference, if you see here, there are many quantum machine learning algorithms. And here, if you expand, you will see trainable model objectives and Pegasus QSVC and QSVC, VQC, QSVR. This is what the regressor. If you select this quantum support vector regressor, this will be used for continuous variables. If your base model is a continuous variables and then you want to perform a numerical regression, you can use this QSVR for performing quantum regression. Hope that answered your question, sir.
yes, sir, definitely. Yes.
Yes, sir. Great. Any other question from other members? The iris features are continuous in nature. How QML has been applied on this state? Madam, actually, we in this QSVC quantum support vector classifier, we use the discrete nature of iris. But if you are worried about it is a continuous nature, we have to use a regressor. You can use this QSVR. Hope this explains your question also. Because for some historical purpose, we started the QSVC, which is the discrete version of your support vector classifier, or we are converting that into a simple model. That is why I demonstrated the QSVC, but it can be done with the QSVR, which is the correct approach for handling the continuous data. Okay, madam? Right. Now, I want to go back to basics now because now I'm going to explain the code and the circuit, how the circuit is formed. Here, you will see how I'm getting the circuit. Ad hoc feature map dot key decompose dot draw. meaning that the ad hoc feature map is a composite object. It is not only having the circuit, it is having other components also. I will show the DAR function of this ad hoc feature. Yeah, when I run this, what you observe, the ad hoc feature, my apologies for some. You see, it is a Qiskit library data preparation, ZZ feature map. So this is the very important point. That's why I told you ZZ feature map. If you can see here in this explanation, I wrote a feature map as a data encoding with the angle encoding approach, meaning that it is used to prepare your data using ZZ feature map. So obviously now you hearing the word ZZ feature map multiple times. Now you are very much interested to know what is ZZ feature map. And if you see the object structure, it is imported from Qiskit, not from Qiskit machine learning. This is the very important source. So Qiskit documentation is accessed here. Qiskit documentation. Under Qiskit documentation, when I go into the API reference of Qiskit documentation, see, for your information, I'm using Qiskit 1.11 because for machine learning, Qiskit 1.11 is compatible. The latest version is not compatible. That is why I am using the older version of Qiskit. So here I am changing to 1. Actually 1.0. I'm using 1.11 that was dropped. Here, if you see the circuit construction under circuit library, you will see insert feature map. You see, there is one Z feature map. There is one ZZ feature map. Z feature map is the first order rotation. ZZ feature map is the second order. So if you read the documentation for ZZ feature map, they are telling that second order Pauli Z evolution circuit. So we can build our own circuit with the combination of superposition followed by a PQC, parameterized quantum circuit. So I'm passing theta 1, theta 2, theta 3, and depending on the reps, the number of repetition, I will have different number of rotational gates. That is the ZZ feature map. If you go to just Z feature map, you will see this circuit is having only one Hadamard gate. Only there is no any entanglement. Only superposition followed by rotational gates. That is what Z feature map. But ZZ feature map has superposition followed by rotational gates followed by entanglement. That entanglement gives the capabilities for second order feature, second order evolution. The important thing is the entanglement can take three forms: circular and linear. Other one is oh my God. You cannot find out that in easy. I will tell you because I used here linear, circular. Other one is okay. I will tell you before the end of the session. I will recall. So there are three entanglement model. So the ZZ feature map is used for second order evolution, which is used to encode your data using angle rotation. Right now, I will stop here. I will wait for some questions. After the questions, I will come back to the next step. Sir, could you explain your code line by line? Then we will be able to rate it more from. Okay, madam. Okay, right. So I'm going to explain line by line. Classical part, you are very clear. I'm not going to explain that one. Is that okay? Let us come to quantum part. So you can see here I started ZZ feature map, which is the first line. Exactly, because I know the flow. Usually that will be the follow-up question. That way I started with the ZZ feature map. Now you understand what is ZZ feature map. Next one is sampler. Sampler is a primitive, meaning that it is helping you to connect to either simulator or QPU, real hardware. In this case, I am using a simulator, which is AER simulator in this demonstration. Because if you give simple sampler without any parameter, it will use a AER simulator. That's what being used for this execution. Next one is the compute and compute. Qiskit underscore algorithm state fidelities, compute and uncompute. And here is the challenge, because it is being imported from a new library called Qiskit algorithm, and it is having a sub object called state fidelities. So now you are interested to know what is state fidelities. Am I right? So let me explain what is state fidelity. So the state fidelity is when you're having a quantum system, the um, the state interconnection. It is actually related states of the whole system. That was the state fidelity. Usually, it is achieved. The fidelities are how to say that relationship or the correlation among all these components are established by sequence of compute and compute operations. That's why there are two operations under state fidelity. So I will show you the documentation also, because that will help you clearly. So that I have to go to again Qiskit ecosystem. Under Qiskit ecosystem, you will see something called quantum algorithms. Under quantum algorithm, you will see state fidelities. Yeah, here is the Qiskit algorithms. And under this algorithm, if you go to ATAL, you will see state fidelities. Under this, you will see base state fidelity, compute, uncompute, and then state fidelity result. So you only these two things are used to as a fidelity. This is the result. Read about what is compute and uncompute. You are reading this one. It is inner product of two quantum systems, and they are obviously normalized, because we are dealing with normalized vector space. Hilbert space, actually. Being these are all operating in the Hilbert space, they will hold the norm or normalization. So this class leverages sampler primitive. That is one thing why we are using sampler with this compute and compute. Two quantum circuits. Here X and Y are operational parameters. So you can't find a lot of explanation here, but here you will see it is a outer product. This is what compute and uncompute. Next, obviously, you have to understand what is your next one is kernel. The kernel is coming from Qiskit machine learning. So finally, now we are coming to Qiskit machine learning, which is already opened Qiskit machine learning, right? The Qiskit machine learning. It is kernel. You see here is quantum kernel. Under this kernel, you will see fidelity quantum kernel. There is a state vector, then trainable. There are algorithms also. We are not going there. Fidelity quantum. This is what we are using. The fidelity quantum kernel is again, it is based on base state fidelity. And if you recall, this is the same thing what we studied in compute and compute. Because compute and compute is based on base fidelity. And here, this fidelity quantum kernel is based on base fidelity. That's the reason why the outer product operation is applied consistently from your compute and compute to your kernel. Okay, now coming back to the, so these 4 lines are over. Adduct dimension, this is the qubit count, the number of qubits. In this case, I'm selecting 4 because I'm having 4 features in the iris. That's my justification, but it can be different also. That I will explain in the neural network after that level. Now, using these components, I am building ZZ feature map with the 4 qubits and 2 repetition and linear entanglement. So as I told you, I can change it to circular also. Then I'm creating the sampler. Then fidelity is created with the sampler. Then passing the fidelity and the fidelity and attack feature map to my kernel. This is what the first section. This is the preparation of your quantum circuit. Now I have to pass the data from iris dataset. That is what I am doing here by creating the model, which is coming from QSVC, which already I started in the algorithm. Yeah, here you see the QSVC. The QSVC, the quantum supported classifier, and this has both fit with the training data set, predict with the test data set. The same way how the classical supported machine is working, the same way it is working. But here the important thing is we have to pass the kernel. The kernel will bring the feature map. So, and for that I am passing training data, which is 105 subjects, both training as well as the data and label I'm passing here. Then see, when I pass this QSVM model and WIT operation, that is where the quantum operation is happening. It forms a density matrix with 150 samples kind of accumulated into one single system. And that is parallel. There is no sequential operation. That is why this quantum machine learning models are promising a better performance compared to classical. But now we are not seeing because this is running on a simulator, not running on a real quantum computer. That is one reason. Then I'm predicting with the X test, which is the 45 rows of my test data. Then I think remaining things are similar to classical. Only these things are all difference between quantum and classical. Now I ready to answer your questions. Any question? Kiran Patel asking, is the screen visible? Okay. Right. Okay, any question based on this line by line explanation? Waiting for a few questions. Feel free to ask question because this is very interesting part. What you are seeing now, it is a kind of how a quantum system is able to encode your 105 iris data. You just to visualize this one. We have 4 columns: sepal length, sepal width, petal length, petal width for 105 subjects, and these things are encoded in one single system parallelly at the same time. That is the beauty of quantum systems. Now, if you compare this with a array-based or NumPy array-based classical approach, which is processing sequentially and then building your support vector hyperplane, and based on the distance between the hyperplane, it is calculating the accuracy. That model is sequential model, but here everything is a kind of density matrix kind of structure, which is 3-dimensional or n-dimensional Hilbert space, a finite state Hilbert space, and that Hilbert space is able to accommodate all these 105 samples or 105 subjects in one density matrix. I'm stopping here because I'm waiting few more questions.
When we use the fit method in
Yes,
your
sir.
code, yeah, when we use the fit method, fit
Yes, sir.
command,
Yes, sir.
yeah, I doubt how the features is that independence or dependence of each other is taken care.
Okay.
You know, the classical, we see that in naive Bayes also, no, in particular. In every model that has to be considered. Oh, yeah.
Correct. That when you are when you have a strong knowledge on classical, for example, I am very confident that you are very good at the foundational concept of support vector mission in the classical world. So you are, I think you are able to visualize how these 105 subjects are added to your array. Then a mathematical operation is performing the classification that you know very well, right? Now we are trying to connect how that operation is being done on a quantum during the fit operation. Correct. Let me explain this with the, I will go to this.
Interdependence of these features, how they are taken care in this parallel model of a quantum
Yeah,
picture.
interdependence is second stage. Before that, we have to understand how this data is encoded.
Yeah,
I mean,
I was thinking about the fitting. Yeah.
the fitting in classical, there is no step called encoding. Directly, our libraries can process our classical data because the classical data are suitable for classical algorithm. But quantum cannot handle classical data. If it is a binary, see, for example, you know very well the iris data set. If I take the first data set, let us take this first data set. First data is 5.1 and 3.5, 1.4, 0.2, right? For a classical support vector machine, 5.1, 3.5, 1.4 will make sense. But for quantum, it won't make sense because the quantum will expect all these things either as an amplitude or as a phase. Now you include the encoding step into your building the interdependence model.
Okay.
Now you got the point, right? When
Yes.
I encode this 5.1 as a normalized 0 to 2 pi, because that is how I have to normalize, because I'm using Z feature map. So I have to encode my 5.1 into 0 degree to 360 degree. So in radian, I'm telling 0 radian to 2 pi radian. Within this one, I have to normalize. So now imagine that I have a football. In that football kind of 3-dimensional sphere, 5.1, it is building a vector, a superposition of a vector in a superposition with a certain angle, not 90 degree, not 0 degree, because those are all base states, but I'm making them into superposition. That's why in the circuit I have Hadamard gate. Am I making sense, sir?
Okay.
Yeah,
Yeah. Yes. Okay.
that is the important step you have to recall. Then that interdependency are formed as an accumulated um, mapping, angle mapping of all your data points, and they are getting added, that 105 subjects. Each subject will change the position of those 4 qubit, because 4 qubit they will be in 16 states at the same time. And the 16 states, for the first subject, it will be certain angle. For second subject, it will be some other angle. And this is evolving. That's why that ZZ picture map is called a second order poly-evolution circuit. It is evolving. That evolution will form a non-Euclidean space structure on. It is like a surface, a football surface, have all data points. Now I am drawing a linear line, but it is not linear because my space is a non-linear Euclidean space. Even though I am trying to draw a hyperplane which is linear, it is going to become a parabola. Then it will divide your data according to your existing or the training data set evolution. I will stop
Hilbert
here.
space, yeah.
I will stop here and then explain. Wait for any question, follow-up question. There is another question from Suchitra madam. Sir, does accuracy and computation will increase, decrease on real quantum computer? Yeah, in real quantum computer, the accuracy will increase. How I'm telling, initial days means when IBM released 27 qubit and 59 qubit and then 72, 71 qubit. During those periods, either in classical or either in simulator, both in quantum, we did not see any difference. But after they released 121, 133, 433 qubits, we started seeing the good performance. But now it is very costly to run on a real QPU. That's why I'm not able to show you on a real QPU. But I tested some of the models, client models, which client has given me a premium access. There I'm seeing a lot of improvement. Day by day, I'm seeing very good performance in quantum real QPUs. Hope that answered your question. Okay, right. So can we move on to the next step? Now I'm going to start. I'm going to give you a few more idea, because when you are building a quantum system, there will be a lot of challenges because it is the amalgamation of various components. Even in this code, you see, I am importing the components from from Qiskit circuit, Qiskit primitives, quantum Qiskit algorithm, and then Qiskit machine learning, and internally Qiskit underscore AER. Like that, I'm importing from multiple packages or multiple libraries, right? So the knowledge of these libraries and then their interconnections and how they are handling these quantum states, or state vector or density matrix or Bloch pair, those things used to be very, very clear. That is boiling down to the foundational concept of Qiskit or any other quantum simulator. Am I right? So, so now we have to go for break, right? 7:30 or 7. Okay, 7:30 to 7:40, we have break, 10 minutes break.
So we have a yes, sir. 7:30 we can have a break. So
Yeah, yes. Yes,
you need some rest, right?
yeah.
Because you're the one who's continuously speaking.
Thanks, madam. There is a question
Yes,
from
sir.
Kusum, madam. Does selection of number of qubit? Yes, madam. The number of qubit is depends on the features. That's a correct understanding. Yeah. Now, what I'm thinking, like, remember earlier I asked the question, what is the very fundamental questions? Like that, I have another fundamental questions. See, we can directly jump into quantum supported transmission, quantum neural network, and QGAN, QPCA, QIPA. So those things are possible. But I have a fundamental question. Do you know how to build a bell circuit without referring internet? That is the very important question. This is the important part. Without referring internet from your memory, can you build a build circuit? How many of you are confident that yes, KG, I can build? Or how many of you have the question, is it possible to build a quantum circuit without referring internet? See, that is one important skill set or capability what I am seeing among the beginners, those who are starting quantum computing. They are able to run the program in their system, but the program they won't type. What they will do, they will search some GitHub, they will find the code, either download that IPyNB or Control C, Control V. We never, or at least 60% of the beginners don't try to build a simple circuit from their memory. I'm not sure how many of you agree with me, but beginners have this problem because I'm mentoring many quantum computing professionals in my because I'm mentoring them to work my project, right? So the first thing what I recommend, can you write a build circuit without referring anything? Your internet is not working, your local laptop, it has a Python and Qiskit. Can you build the build circuit? Okay, this particular skill set will take 15 minutes. If you are interested, after the break, I will show you how to build a build circuit without referring any help and from top of your memory. Then that will give you a confidence. Yes, this is how we are writing the quantum program. Then I will go to quantum neural network. Then I will go to quantum inspired approaches. Is that okay? Or else, if you are interested, I will directly jump into quantum neural network. Think through this one. Please come after break, type in the chat window. Based on that, I will plan the approach. Okay, thank you. Have a break for 10 minutes and then come back. Bye-bye.
Thank you, sir. ಫಾದರ್
ಅದೇ ಆ ಯೂನಿವರ್ಸಿಟಿಗೆ ಅಕ್ಕ ಓಕೆ ಹಂಗ ಗೈಡ್ ಮಾಡುದು ಓಕೆ ಅಂದ್ರೆ ಅಕ್ಕಗೆ ಸರ್ದಿ ಬೇರೆ
Okay, can we start now? Can we resume our session? Okay, right. So,
Yes, sir.
okay, right. So,
Yeah.
Madam, Deepa, Madam, if faculties are interested to connect with me, you can share my number, and also you can connect with me in LinkedIn.
Sure, sir. Sure,
Yeah,
sir.
follow-up question if you need any support in building your proposal or project, I can support. So with this one, let me, as Kumaravels are asked about bell circuit. This one I'm going to demonstrate using Google Colab, because most of you are comfortable with the Google Colab. Let me start with the Google Colab. Because it is much easier. Start a new notebook. Um, so when you start a new notebook in Google Colab, you know it is not having any packages, correct? So you have to do install skit space skit -AR space um, matplotlib latex enc. These are the important if statements. So I'm going to run and I'm going to share this in your chat window. So you can practice along with me. Oh, sorry, I will share my screen. Sorry about it. Okay, hope you are seeing my screen. And I shared this pip install command into your chat window, and you can start your Google Colab and run this pip. It will take few minutes or few seconds depending on your network. For me, it is already, I think it is completed. Yeah, it is completed. Since you are installing the PyLatex ENC, it is necessary to go to runtime and then restart session. Okay, after pip install, you have to runtime restart session. Now I am minimizing this one, hiding this one. So now I have installed all these packages. Next, I am going to from his kit port quantum register, comma classical register, comma quantum circuit. These three components I need. Now I'm building the quantum register. QR equal to quantum register of 2 qubit, because bell circuit needs 2 qubit, and CR equal to classical register of 2 qubit. QC equal to quantum circuit using QR and CR. I think this is straightforward, easy to understand, no confusion. Now I have to build the bell circuit. What is the bell circuit? Hadamard gate followed by CNOT gate. So QC dot Hadamard for QR of 0, meaning that, okay, I will show a bell circuit here. Bell circuit as an image. You check an image, you can see here a bell circuit is Hadamard gate followed by CX gate. That's the reason why I am using Hadamard gate for QR01. QR has 2 qubits, right? 0 and 1. I'm using the subscript or index. Then QC of CX, controlled NOT gate. Control qubit is QR0 and target qubit is QR of 2. Now QC dot measure QR comma CR and draw. That's it. Only 7 lines. This will design the circuit. I'm not going to execute now. I have just designed the circuit. Now, if I run, you will see the circuit is drawn like this, but the look and feel is not good. So for the draw, I am passing MPF, a matplot based approach. Now you will see the circuit. I will stop here and everyone try to type it. Don't Control C, Control V. That is what the goal. After your pip install is completed, you can have this circuit design. I will give 1 minute for this one. Okay, 2 minutes. Any question? You should be able to see the circuit. So far so good. Timer. I think no question. The 10 seconds. Now the circuit is built. I have to execute this one. To execute this, either I can use a sampler to directly run on a quantum processing unit QPU, or I can use a simulator. So for that, from discrete underscore AER import AER simulator, and sim equal to AER simulator, and job equal to simulator dot run QC, the circuit what we built in the previous cell. Then result equal to, from job I am getting my result. Now the output equal to result dot get counts. Now if I print output, you will see two output, 1150700517. So in this execution, we have 00 as the output because it is having higher number of probability or higher number of occurrence. Now this visualization is not because the dictionary is not looking good. I want to visualize. So from escape.visualization, import plot histogram out. Now it will draw the histogram. This is what a typical Bell circuit program. So here we designed the circuit. Here we executed on a simulator and visualized using a plot histogram. Now you are seeing, right? I will give 2 minutes for you to complete this code. I will share the code at the end of the session, but now I request you to type from scratch and in your Google Colab. You need not worry about configuring anything in your system. All good? Any question? Feel free to ask me. We have 1 more minute. Oh, okay. First part not completed.
Will the count will be same for
No, the sound
all the
count
runs?
should not. No, it will be different because it is purely random. Each one will have different number. You will not have the 507517. So don't expect that count to be same. If it is different, that is the real output.
Thank you.
The 2 is the number of qubits, because Bell circuit needs 2 qubits. So I'm using 2. If I'm building a GHZ, which is 3 qubit, I will use quantum register of 3, classical register of 3. And if I'm going to build 4 qubit quantum Fourier transform, then I will use 4 qubit. So for initial practices, I recommend these gates: Bell circuit, GHZ circuit, and QFT, QPE. Yeah, I'm going to type here because it is not disturbing your working also. So practice these circuits: Bell circuit, GHZ circuit, 4 qubit quantum Fourier transform, and 5 qubit quantum phase estimation. Um, then you can go for DJ, then Benson Vazrani, Simons, then Shor's. Oh, this is the right order of practicing quantum algorithms. Before jumping into advanced quantum machine learning or quantum optimization, quantum inspired simulation, I strongly recommend build these circuits confidently. You should not depend on any internet. You should be able to type these programs from your memory on top of your head. I'm not asking to memorize. That is very, very important. You should not memorize. You should understand the 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 quantum gates and their way of transforming your qubits into the necessary operation, and at the end giving expected outcome. Okay. Yeah, time up. I believe I will stop here. Then now we'll move to quantum machine learning. If you have any question, I'm ready to answer. Before jumping into the quantum machine learning, quantum neural network, and then quantum inspired algorithm. Yeah, we have sufficient time to cover both. Any question? Okay, no question. Great. Now, see, we learned quantum support vector machine, right? Now we have to learn quantum neural network. And the quantum neural network is the very important part of quantum machine learning. And indeed, it is not only for quantum machine learning, it is an essential part for quantum artificial intelligence also. The way how quantum neural network is working, first I will explain how it is working, then I will show you an implementation part. Because without understanding how it is working, it will be, how to say, it's not the right way to learn. So, so let me take in a blue color I am drawing, right? So the classical neural network is a fully connected network, right? That is what a classical neural network is. So each node are connected like this. Not going to draw for everything. Just I'm giving the initial steps, and I will do the final steps. It is familiar to everyone. All of you know this one. Then This is what a classical neural network. So in classical network, what is happening? There are three components. One is input. Next one is hidden. The final is output. Am I right? So in quantum, if I'm able to build this input, hidden, and then output, you will at least start believing that yes, neural networks are a component which we can implement in quantum also. So here, I will draw these things in a green color. So we have zero ket, like the qubits are initialized with the zero ket. After that, we will do something called encoding. Or like this. Encoding, right? After the encoding, this steps forms input layer. After encoding, what we will do, let me draw the line like this, then only it will be easier for you to. So here I will build next part, which is few rotational gates or any number of rotational gates Rx with eta 1 Rx. See, Rx means it is not X rotation, any rotation. Theta 2 and n number of rotational gates with n parameters, theta n. Then this will be repeated as per my requirement. So this will be repeated depending on the number of hidden layer, how we are keeping in our classical. So this rotational gates will be repeated. Sometimes after that, at the end, we will put conditional or entanglement. It may be partial entanglement or circular entanglement or linear entanglement, whatever it is, whatever works for our algorithm, use that kind of entanglement. And now this whole step will be repeated as per our requirement. This is called hidden layer. This is what the output. The output is implemented as a set of measures, like each qubit is measured at the end of your rotational gates and then entanglement. This forms your output. Is it clear how neural network is implemented in quantum? This underlying structure is very, very essential. And if you want to know more about this one, I recommend a YouTube channel by Jay Shah from our organization, Boson QSci. You can see a detailed explanation about how quantum computers or how a neural network is implemented in a quantum systems. Is this clear? Any question here? Now I'm going to show the code. Okay, right. No doubt. Now I'm going to build. See, I have multiple programs, quantum neural network based programs. but they are all very big, meaning that they associated with the domain problem and the data processing, all those things are involved. So what I'm going to do now, I'm directly going to show you the neural network implementation in IBM Qiskit and also Penny. To speed up the time, I'm just directly going to the respective documentation, API reference, and then I will point out this is what that neural network implementation. So that will speed up time because we need time for what is called our quantum inspired approach also. Is that okay, or you want to see a full-fledged quantum neural network program? Please type in the chat window, but I will start with this explanation because anyhow that is necessary. So I'm going to open here. Let me go to quantum machine learning. It is here. Under QSVC, there is something called, you see here, QNN circuit. This QNN circuit blueprint, it is a blueprint that wraps a feature map and answered circuits. And wait a minute. There is one more thing, two local, one local. That's what I wanted to show. Because that is not straightforward. It is here, yes. A neural network, a QNN using estimator, a QNN using sampler. See, this is two different approaches, estimator and sampler. Sometimes we will use estimator, sometimes we will use sampler. When to select estimator, when to select sampler is beyond the scope of today's session. If anyone interested, feel free to connect with me. I will explain you in whatever way possible. So let us take the neural network as a simple one. If you take this neural network, it has the implementation, number of input, number of weights, output shape, and then gradient. It's surprising to see, right? All important components of your neural network are being passed as an attribute to this object. I don't know whether the sample program will be here. Sample program is in the GitHub. That's what I have to show. But now I'm going to do it in a, remember just now I built this Google Collector. Here I'm going to do it. So now, my God, I need to import Qiskit machine learning. So I will come to this program because it has the machine learning. So here I will continue doing that program. So Qiskit underscore machine learning dot. Now you figure it out, right? How if I want to bring that neural network, I have to bring it from Qiskit machine learning dot neural network, right? This is how I have to bring it. Neural network, neural networks, import, right? That is the syntax. That is the syntax. So now I imported this one. Now any spelling mistake I made? Cannot import neural network. From mistake I made. Okay, then I will take the program because it will take some time here if I solve that one. What is a GitHub? Here you will see the code. This is older version, so you can directly use this one. Little bit changes is required. Discrete machine learning, discrete circuit parameters. So this one, you see the old version where they implemented everything from scratch. So for any reason, if your existing import is not working, you can come to this implementation also to get those idea how this neural network is implemented. So since it is taking this kind of time, but I wanted to show you this is from scratch. If you want to build something from scratch, it is possible to go to this level of library, and then the documentation. From the documentation, you can build your whatever objects or whatever components you need, you can build it. So I want to confirm whether this Qiskit machine learning version is 0.83. That is also you have to make sure your Qiskit machine learning library 0. See, I am referring 0.83. Sometimes you may use the older version. Make sure that that is also covered. You will directly use a neural network classifier. And if you want to use neural network directly, you can use go to dimension. They are all using only the QNN circuit directly, and the neural network classifier depending on your problems. So here I would like to learn machine learning. That is what I showed earlier. Convolution neural network. Here also there is an implementation. Again, here there are also neural network classifiers. So in the latest version, the quantum neural networks are QNN circuit and neural network classifiers model. I would like to stop here and answer your questions before jumping into showing. Remember, I told you I have few programs. Before jumping into that program, I want to stop here and then show what is the questions you are having. So this one, now I'm going to run this one. Any question before jumping into the option? Oh, the YouTube channel, it is J Shah. It is called neural network, quantum neural network. Search this way, you will find it. Now coming back to, first let me try this one because not very much different, because this version's compatibility issue will come. Here, whether it is showing anything. Let me do in QC. I have to build here. It is there. The QC circuit is the rotational gate, all those things. I'm passing the weight, and so finally the QC is available. This is my QC2, and here I'm passing. Quantum circuit is not defined. Oh, this one is, I did there. Okay. This is my circuit, and here I am building my my network. Neural network is implemented as a few set of rotational gates and followed by entanglement. Remember, this is what I implemented as a neural network. Now I had my sampler QNN is ready. It is the simplest way to build a neural network. I will stop here, answer your questions before jumping into a full-fledged implementation. Any question? I'm expecting a few questions because the implementation of neural network, you can see here, I built the circuit and it is directly connected to this explanation. And here the encoding part and then initialization part is not implemented. The reason is that I am demonstrating a simple one. And the parameter, those things will take care of that encoding part, meaning that I'm using the basis encoding. So literally I need not do anything. That's the reason why you are not seeing any encoding part exclusively. Only the hidden layer you are seeing. The output layer is measurement. When I run these things in a, see now this is QNN only is formed. Now I have to run the circuit and then measure it. That which given here in the how to run a back forward pass in the sampler. In this one, you will see how to run the sampler forward. And this one I have to run, then it will be a forward pass. Sorry, I forgot the previous step. It is setup, I forgot. This is my sampler given an input. Correct. Yes, that's correct. Still input is missing, right? Here. This is the input and the okay, now again another library I have to build. It's not it will expand. If I reach the cells, it will expand. That's the reason I'm stopping there with the just implementation is sufficient. And I can see the sample QN and what is active now. This one you see here. If I try to DIR this sampler QNN, you will understand it is having all the components. Inside it, there is a circuit. So DIR sampler QNN dot circuit. And here it will be a circuit. So now you find out the circuit. So sampler QNN dot circuit dot draw. Without decompose and draw, right? You see, it will show a kind of the circuit what we draw there. But I want to decompose, then draw. Decompose, then draw. So this is one important step we have to understand. See, when there is no, you are seeing this one, right? Let me run it without decomposition. So decomposition, you will see that it is directly showing RY. So, but internally, how it is doing? It is passing a parameter pi by 2, a rotational gate with the pi by 2. That is how the real implementation is going. See, that is the advantage of decompose. When you find out this is my quantum circuit, either you can draw the circuit as it is with a black box approach, an oracle approach. But if you want to go deeper into that actual implementation, you can decompose it and then draw it. I believe this particular 4 cells will explain you with a, how to say, a 10,000 feet level. In my opinion, that is sufficient. You don't go deeper into those things, than implementation, all those things on beginner level exploration. Any question? Okay, right. Now it is 8 o'clock. We have another 1.5 hour session. Before jumping into the quantum inspired and then quantum simulation. I would like to answer your questions. Any question? I'm expecting. Okay, right. If no more question, let us continue with the next step. So now I would like to go back to a PPT, because now we are going to see some concepts. It is here. This is your. I think in QML also I have not completed in full. Let us continue this QML thing. So now this is the challenges in QML, because now you have seen that the QML accuracy is not good. It's not sufficient. The speed also, the performance is also not good. Why? What are the challenges? The first reason is quantum computers are still in the nascent stage, and the quantum algorithms are very difficult to understand. See, that is the reason why I gave you these circuits to practice. So if you practice these circuits, then the complexities will start fading away over a period of time. It is, as I told you, don't rush learning quantum computing. Plan minimum 9 months to 12 months, 3 to 4 quarters. You need that much of time. And in my opinion, and in my observation in mentoring multiple professionals who are working on the quantum solution, building quantum solutions, it needs this much of time. That is how we hire an intern, make the intern familiar with all these programming concepts, infrastructure, Linux command, and various ecosystems, both software, hardware, and how to import these libraries, how to run either in Collab or in your local system or in directly in a Linux system. Then we will come to this basic algorithms. Then basic algorithm with a multiple, after that only we will put them into a real project, building a proof of concept or prototyping. So that's based on that I'm telling. Keep sufficient time to learn all those things. Don't hurry, don't rush up. It will need some time to comprehend the concepts before jumping into building a solution. There is a reason. The reason is that you see here, the field is young and rapidly evolving. Continuous learning and adoption. I will tell you the reason. The continuous learning. Why I'm telling the continuous learning and the adoption. When IBM introduced their Qiskit in 2017, 2000 end of 2016 for the public, Qiskit machine learning was not at all in their ecosystem. And it was one single Python package, just pip install Qiskit. And after some time only they introduced Qiskit algorithm and then Qiskit simulators. Prior to that one, they kept everything in one single package. That time they followed the architecture. Remember, Terra, Ignis, Aqua, Air, these 4 components. Like that, they formed into one simple package. That's what IBM released. But later they separated this Aqua into a separate component. Terra is not at all available. That moved to hardware layer. Then Ignis AER are only available interface for communicating to hardware. That is how they released in the subsequent versions. But now, if you see, surprised to see the latest version of his kit is having where is this one? Sorry, I want to show this one. Yeah, sorry, my bad. Okay, no problem. I will go to quantum Qiskit documentation. I want to show that one because this is Qiskit documentation, and I'm going to my reference SDK. You see, C libraries available now for general public. Earlier, Qiskit SDK C version is available only for premium users. This is a great change in the way how IBM started giving us C or implementation of quantum programs. With the C library, now we are really very happy such that we can, instead of Python, we will use C. This is an amazing enhancement happened in version 2.1. This is what I'm telling, the continuous adoption, continuous learning and the adoption is necessary to become expert in any quantum field, either optimization or quantum machine learning. Okay, right. So be prepared for the continuous learning. I know this is theory. It is not directly to the quantum machine learning. Oh, any book, please suggest roadmap for QML. Yes, I can give you the clear roadmap. Oh, till 9 only. Sorry, madam. I thought that is 9:30. Sorry. Okay, okay. I will finish. Then I will reduce my history, then directly go to the any book for, yeah, I am going to share that one. Sorry. I thought that it is 9:30. Now, this is very important. As I told you, quantum machine learning needs data encoding, very important part. There are 4 encoding method, which is basis encoding, phase encoding, amplitude encoding, density matrix encoding. In this, density matrix encoding is the powerful one, and you can see it is used in multiple applications. And in QML, we are predominantly using phase encoding and then amplitude encoding. See here, you will see the notation alpha 0 cat plus beta e power iota theta. The theta is what I was referring, normalization of 0 radian to 2 pi radian. That is what I mentioned here. Here it is the probability. The probability will hold your data. That is, encoding is very important part in machine learning. Not only in machine learning, any quantum computing. I strongly recommend spend sufficient time to understand the quantum encoding. Then there are various quantum approaches like variational quantum eigensolver, QAOA. Why I'm giving this one, and then this one is taken from Maria Schuld book. Here, the number of different types of encoding, and this is a typical QML circuit which falls under PQC plus VQC. PQC means parameters quantum circuit. VQC means variational quantum circuit. See, here you can see this is a PQC. What you are seeing here is a PQC, the input qubit, and there are set of rotational gates with omega. This omega is your parameter. Usually it is a theta. And that one is used here as a variational quantum circuit. PQC inside a VQC is what your QML circuit. So when I say PQC plus VQC, initially you may not easily understand what is the PQC, what is VQC. PQC means parameterized quantum circuit. VQC means variational quantum circuit. The word variational indicates we have quantum circuit with classical component. The classical component is used to calculate the loss or cost. Based on that, another classical algorithm will optimize your parameter, the theta or omega, that is passed to your PQC, parameters quantum circuit. So, in my observation, all quantum circuits are VQC, meaning that there will be always some classical component encompassing, how to say, your quantum algorithm will be a part of a classical algorithm. That is always. That is the reason why we confidently telling that a quantum computer will not replace classical system. It will be always CPU plus QPU. So this, remember this PQC plus VQC. And now how this learning is happening. This is the important part. Remember I told this is iris dataset example. You have iris dataset. After the pre-processing, you are passing to the feature map. The feature map is encoding your subjects into density matrix, accumulated density matrix by repeatedly passing your training set. Then the quantum kernel is used to build your overall quantum system, which is passed to your QSVC, quantum support vector classifier. And this is what I mentioned sometime back. Kumar sir asked, right? So this is the representation Even though you are using a linear classifier or linear hyperplane to classify your data, to segment or group your data, that is going to implemented as a non-linear implementation because we are using Hilbert space. Hilbert space, it is a being the normed complex vector space. It is converting your linear hyperplane into a non-linear classifier. And this is applicable to all classifier circuits. But quantum neural network is what I showed here. This is very important understanding you should have. See, this one is quantum neural network. Quantum neural network also using the same thing, but not in the classifier model. It is using this entangled, and at the end of the measure, when you remember, this one is when you measure a quantum circuit that collapse to classical state. That approach is used to implement your neural network measurement. Whereas in classifier, a linear hyperplane is performing non-linear classification. That is what quantum support vector classifier implementation. But surprising to see both circuits look similar initially, at least for beginners. But there is a lot of difference. The way how we are measuring, the way how we are rotating and then performing the conditional entanglement, those things are different. That will result in a different operation. That is where the knowledge of mathematics come into picture. When I will deliver sessions for students, I used to tell you have to learn mathematics. Students don't like that particular line. You have to learn mathematics, but that is essential to understand how these underlying operations are being performed. Okay, with this QML is over. Now I'm going to focus on quantum inspired approach. Before that, I ready to answer any question. Okay, there is a question. Suggest roadmap for QML and any big for QCL QML. Okay, right. Now here is the book. These two books for mathematics. I have studied both books. My recommended order is The Essential Mathematics by Woody is first book, followed by Scherer. First read this book, then read this book. But before reading all those books, oh my God, I don't have this book here. Before reading all these books, I have a strong recommendation to do two things. I will type in the notepad. Join the MOOC course in Coursera. The course name is Learning How to Learn. This is a course. Barbara Hoechley, the teacher name. Your professor name is Barbara Hoechley. Join this course. It will need 15 days to complete the course. And then whenever you go to Coursera, try to search for this one. They will start the batch either that day or next day. It is one of the famous course. Complete this course. After that, read this book. 17 equations that change the world. Read this book. These two things are essential before jumping into any of these things. Obviously, now you understood why I suggested 9 months to 12 months. These two books are mathematics and these books for quantum machine learning. Strongly recommend to read Maria Schultz book. Madam Maria Schultz written two books. One is supervised learning, other one is unsupervised learning. Read both books. And Peter Wittek book is amazing beginner level book. And this Santanu Kangli, it will give you the practical coding. So these three books are I strongly recommend. And there is one ebook called by Frank Zeckert. I not mentioned this one. Frank Zeckert. Yeah, this is. I believe it is correct name. It is available as the ebook only. It is not a paperback. Search for Frank Zeckert QML. Search now itself. Yes, PyQML. Yeah, Zickert. Sorry, the spelling is Zickert. Buy this book, maybe some $6 or $16. I'm not sure. When I bought, it was $6 that time. It has a free version also, but I strongly recommend to buy paid version, because these books will come with your name printed here. My book he printed in my name, so I cannot share that one. Okay, where is this one? It's not this link. There is a separate website for QML, PyQML. Okay, now you understood, right? This is what I'm referring. You search for this one, this PyQML, hands on this book. Search. This is a good source for those who like and practical implementation. Okay. Then coming to the books, and yeah, this is the repeat. Yes, and a roadmap is that strong. You should be a strong classical machine learning. There is no how to say, that is the essential part. Then you have to identify which approach you are using. My strong recommendation is that VS Code and Jupyter Notebook. I don't recommend Jupyter Notebook, but for teaching purpose, we have to use Jupyter Notebook. Then, okay, these are all, I kept it as I thought that you asked Steve. So as a roadmap, what I recommend, I will type here in the notepad and then share this. Step one on classical machine learning, on Qiskit and Penny Lane. Third, learn all basic algorithms. Some practice. Then, yeah, I strongly recommend to start with PyQML by Frank Zickert or Santanu. And recently, Santanu Ganguly and two more authors released another quantum machine learning book. I yet to read that book, but if anyone have that opportunity to buy for your college library, you can buy that book also. You search for all Santanu Ganguly books; they are all really good. Is this helpful? Any question? There are some. Okay, there are some forms. Yes, madam. I will share this notepad. I will now itself. I will share this as the chat window message. You will not miss any information. Okay, I did that one. And as I strongly mentioned, you can connect with me. Uh, Search for this name. I'm from Quantum G. So you can connect with me in LinkedIn. So now moving to the next step. Can we move to next step? Because we have only 30 minutes left. Now I'm going to show few quantum inspired approaches. Now you may wonder why suddenly quantum inspired. What happened to quantum machine learning? What happened to quantum computer? Why when we have 1121 qubit IBM systems, why we obviously, just now you saw, right, the performance is not sufficient and industry cannot wait IBM to release 10,000 or 1 lakh qubit. Correct. So when we wanted to build a solution and then bill our client and then get a paying customer, see, revenue is important, right? So it is an out of necessity. When quantum industry wanted to build something for immediate consumption, we started building quantum inspired algorithms. See, you may wonder why I'm using the word we, because I'm one of the person who built one of the earlier quantum inspired commercial solution. I'm very proud about that one. So now that product is being sold in the market. So even before a real quantum computer is coming, we are able to build something, a production quality. That is what the power of quantum inspired. That's the reason why we included, Madam asked me to include the quantum inspired algorithm. That's what we are going to see now. And here I want to show you applications. Finance, healthcare, logistics, AML. These are all the 4 areas where we can find applications for quantum inspired algorithm. You can see here it is not having any simulation or any real quantum based for what is called the weather forecasting. Those things you cannot see here. Only optimization problems only we can see here. And we have quantum inspired neural networks. We have quantum annealing based algorithm, and we have quantum inspired evolutionary algorithms. And that these are all the things available now, which I'm going to show now. So the motivation for this one, quantum computers are not widely still in the infancy. So that is the one reason why. Actually, this is to remove this one. Yeah, these are all the things why we need a quantum inspired algorithm. So now you may wonder, is there any solution available as a quantum inspired solution? So that's what I'm going to type in the notepad, and then um, we have first the popular one is PQ5, PQ5 QIEVO. So what's the company name? BQ5 is our platform. BQ5 is our platform. Product is quantum inspired evolutionary optimizer. This is our product. And any of the faculty are interested to explore and test this BQP QAEO, please connect with me. I can get license because I can get you free license for 2 months or 3 months. If you proved that one, even I can closely work with you, help you to move your proof of concept to the product. That level of support I can do. If you start exploring this BQ5 QAEO, feel free to connect with me. Second one is Microsoft Quantum Inspired QAEO. Sorry. Quantum, sorry. Quantum Inspired Optimizer. Then third one is Toshiba SQBM Plus. Then fourth one is Fujitsu Digital Annealer. So these are the 4 products available in the market to build your production system as of 2025. I believe this is valuable information, which I'm not sure how many of you know this information, but this is very valid information. If you are submitting any proposal to NQM or any other body, and then they are expecting TRL 6 or above, you cannot build on quantum systems, because still quantum systems are under TRL 3 or 3, 4, maximum 5. That is beyond that, quantum systems cannot go because they are not ready. But if you build something using these platforms, they can go to TRL 6 or 7. So this is very useful information. Some of you may not know. So with this theory, now I'm going to show you 3 programs which are based on this quantum inspired algorithms. After that, we will have, I'm planning minimum 15 minutes for Q&A. So feel free to ready with your question, and you can type the questions now itself, such that after the demonstration, we will have some time to answer your questions. Now I'm going to share those 3 programs to Madam. Madam, please share with all the faculties.
Sir.
I'm sending 3 files to you, Madam. Have you received, Madam?
Sir, I have received it. I'll share it in the group.
I shared with
Sir.
Madam Deepa,
Sir,
Madam,
can you
in
hear
WhatsApp.
me?
Yes, Madam, I'm hearing you.
Okay, I have posted it in the group now, sir.
Oh, okay, right.
In the WhatsApp group?
Okay, Madam.
I have posted in the WhatsApp group. Is that fine, sir?
Yes, Madam. Yes, Madam. It's okay because this is
Okay.
for demonstration purpose. There is no any IP involved in these demonstrations files. No
Yes,
problem.
sir. Okay. Done,
Okay.
sir. Done.
Great. Thank you. And these programs will give you some confidence because let me take this first program, quantum inspired evolutionary algorithm. I think this is what first initially we were discussing, right? That question came in the beginning. Now I'm going to, you see here, I'm having only NumPy. Already the pip install NumPy is there, but for the completion I'm keeping. I'm having only NumPy, and then I'm having 4 functions. One is initialize population, and it is a random initialization. Here I can use Hadamard gate. When I want to initialize a population randomly, Hadamard gates are ideal quantum random number generators. I'm not sure how many of you agree with me, but if you have a n qubit, Hadamard gate of n qubit will generate more accurate random number generator. That's why the classical random number, which are PRNG, pseudo random number generator, are being replaced by quantum random number generators. And for this one, there are real hardware products which are working on photons. Even we don't need quantum computers. They are just a simple superposition of photons or any other quantum system. They will generate the real quantum numbers. Those QRNG are popular products which are available in the market. So some that kind of quantum concepts can be used here. But this is a classical where I can bring the quantum. That is where you see here, I commented these operations. 0 ket equal to complex number 1 comma 0 j, and superposition is 0.707 0.707 j. Then I can apply a theta theta over 2 times 0 ket plus sine theta over 2 times pi. So like this operation is a quantum operations. One thing what you are noticing this one, it is able to make your data a quantum superposition. And to some extent, we can do entanglement also, but we cannot do interference. That is the limitation in your quantum inspired approaches. Quantum inspired approaches can have superposition and entanglement. Interference cannot be included this one. And any natively parallel processing algorithms cannot be implemented. Why? We are utilizing the quantum behavior in a classical system. And classical systems are natively sequential. They are not parallel. So if your algorithm can leverage the computing capabilities of superposition and entanglement in a classically sequential approach, you are ready with a quantum inspired approach. Is this clear? But for completion and easy to understand, I'm using all classical approaches here because that will run very fast. And some of the quantum approach I cannot share because, as I told you, we have built our own products and then we have some of the IPs. So that is one thing. I should be very careful about those things. You cannot find in the, even if you Google on the very limited information only you can find on the quantum inspired algorithm, because most of the information are IP. And here you can see I'm calling QIEA, quantum inspired evolutionary algorithm. And that quantum inspired evolutionary algorithm has a population size, dimension, generation, and that theta, which is that important parameter to manipulate your every population. Then we are calling the initialization, then finding the best individual. Then by generation, I'm performing a quantum rotation, which will result in a after completion all generation, I will get the best population or best individual from the population. This is evolutionary algorithm. Let me run this program because you will see it is working as expected. So best solution is this vector 0.9259179963. And we have 5 dimension, right? Because in the 20 population size and 100 generation, I am building a 5-dimensional or 5-dimensional component, which is the vector size. I am having 5 elements in my vector. And I found the best solution. In the 100 generation with the 20 populations, there will be a huge number of vectors. Out of that one, within 5-dimensional vector, I am getting this is the best vector. And the fitness of this one is 3.33. So if you are from early evolutionary algorithm or meta heuristic algorithm background, you can understand how this quantum inspired approach is helping to build evolutionary algorithm. Next, I'm going to discuss genetic algorithm. The difference between evolutionary algorithm and genetic algorithm is that genetic algorithm will have crossover and mutation. And other than that, it remains same. The quantum rotation is replaced by mutation and crossover as a typical genetic process. So remaining things remain, and the parameters also remain same, you see. But here we have, instead of theta, we have the mutation rate. So by manipulating these things, I can find out a best solution for this. Okay, let me execute this one also. Let me do output first. Yeah. You can see my output is cleared. Remember, sometimes back I have 11110, right? Now, if I run, I may get something different. Earlier, I had only 5. Sorry. Earlier, my best solution was a 5, but now my best solution is 4. This is how the genetic algorithm is working. The quantum inspired particle swarm optimization. The PSO is simple process because it is only one, but it has swarm size and iteration. Then there is 3 hyperparameters W, C1, C2, and these are all passed to this QI PSO with these parameters. Then initially I'm preparing everything as a random. Then I'm copying the best position, then apply along the axis. This is the NumPy operation. Then personal best position. I believe most of you know what is PSO. If anyone don't know, let me know. I will explain. Okay. Now, as I planned, we have 15 minutes for Q&O. Elitism available in QGA. Formative session. Thank you, sir. Okay, right. Repeat the part where you are mentioning about the stage, which could be replaced with a QA. Yeah, right. I will show you. I explained you in evolutionary algorithm. This part you see here. This a quantum approach where I'm using superposition as the complex number and I'm performing the superposition operation using, see that I believe that you remember this formula. Go here. See, most of us know this formula, right? Where is that one? Yeah, most of us know this formula. I ket equal to alpha 0 ket plus beta 1 ket. But implementation formula is I ket equal to cos theta over it plus power iota phi over 2 times 1. This is the implementation superposition. In many systems, superconducting, most of the system, they are not using alpha 0 ket plus beta 1 ket because we cannot manipulate alpha and beta, but we can manipulate theta or phi. That's why if you remember the Bloch-Pierre, this is the actual psi-ket superposition formula, which is used in the implementation. So that formula, based on this formula, I'm using this operation. Hope that answer your question.
Yeah.
Any question? Good. Next one is elitism available in QGA. Sir, I'm not very clear about that elitism.
No,
Uh,
when
Go ahead,
in
sir.
GA,
Uh,
they reserve the elite candidates reserved. No? For a king family or minister's family will not come enter into the population. It will remain in the next population also. That is called elite people to be preserved, elite candidates.
Sir, elite candidate will need persistency, right, sir? We need persistent storage. But when it comes to real quantum, we cannot bring the elitism. But in quantum inspired, we can bring, because mathematically it is possible, but I have not used the elitism.
The concept is there or no?
It is easy to bring it, sir. The moment you explained, I understood it is possible to bring it, but I have not implemented. That's why I don't know earlier. But after you explain elitism, I realized that it is possible to bring it.
Okay, sir. Another general question.
Yes, sir. Please, sir.
In your slide, the just now you have shown slides black color.
Yes,
Yeah.
sir.
In the application slide, the fourth statement is somewhat odd man out.
AI and machine learning, sir.
Yeah, the first three lines looks like application. The fourth one looks
Yes,
like
sir,
odd man out. Yeah.
maybe you are right. Your observation is correct. But I will tell you why we brought it in the inspired algorithm. It is not optimization problem, but if you remember the feature selection, it can be mathematically modeled with the superposition and entanglement. If you recall the neural network implementation, where I am using only rotational gate and entanglement, and that two operations can be implemented the quantum inspired approach, and that overall infrastructure or overall function can be used for any other purpose. There is a way to use that for PCA, principal component analysis. That is the reason why I brought it here. Indeed, I'm very confident, and then I have example for this one using quantum inspired algorithm. for the quantum machine learning.
Yeah.
Hyperparameter tuning is a different case, sir. Your observation is very correct, because all other are optimization, and obviously meta heuristics algorithm will cover there. But in AIML, meta heuristics approach is not used. But the way how a superposition and entanglement can help you to achieve some other capabilities, we are exploring that one under these two lines. Good catch what you have found it out. And here I would like to confidently tell you that these two things are possible with the quantum inspired algorithm.
Okay,
And
sir.
this is not any ChatGPT generated output.
Yeah.
I want
My
to make
question
sure
is also not generated by ChatGPT.
it is my own content. I enter this content based on my working experience.
Yeah.
Yeah.
Right.
So it is possible. And if you are really interested to know, feel free to connect with me. I can give you the mathematical model, how this hypertuning. For this one, I want to explore about the classic. There is a company called Classic from Israel. Their website has few use cases which you can understand. I will type their URL, asic.io. This is the website. And some of their problem will help you to understand. And then there is one more website which is based on some, uh, right, sir, that
Yeah.
spectral, the spectral theorem based optimization problems are there, sir. They are used in the supply chain management. That problem also using quantum inspired approach. That is where this fine tuning will come into picture. Good catch, sir, because this is right pointing out, because thank you. Good going. Any other questions? Okay, if no more questions, I would like to share few more approaches, or how to say, quantum machine learning applications where we can implement those things, particularly quantum inspired approaches. So think about this way, FPGA based quantum accelerator or single board computer based quantum simulators. These things can be used to build something called digital twin or IoT automation, or actually few sensing applications are there, but they are not available now. To simulate that sensing, those operations can be done with those real hardware systems. And on top of that, a quantum inspired approach will help you to read input from these simulated accelerator or SBC systems and build a optimization model or fine tuning model on top of that one. That is one approach being explored by multiple projects which involve digital twins. That is one thing which you can consider for any proposal when you are submitting NQM proposal, because there are two NQM proposals are completed. Now one MATI proposal is active till 15 September, but that is for PQC. And there is one active startup proposal active now, but the startup are free to associate with academic institutions. So that also you can find out some startup and then join with them and then submit. That is open-ended. There is no any time limit for that one. So these are all various opportunities for institutions to submit proposals for quantum domain. And there is one more thing. Since MATI is active now, the PQC, post quantum cryptography, there also, because PQC is a classical algorithm, internally it will use the mathematical models like lattice code or group or hybrid approaches. And there also there is a possibility of using quantum inspired algorithms. but that one is deep mathematical model. You have to remember those things, and you should be very strong. There is one more field which is based on geometrical algebra. Geometrical algebra is one field where quantum computers can solve a lot of problems. I'm not sure how many of you very good at geometrical algebra. That's just geometric algebra only, not geometrical. Default algebra is an algebra that can represent manipulate geometrical objects such as vectors. So it has lot of potential. Quantum computers have potential to solve many geometric problems because um, some of the geometric problems are exponential problem. That is one thing. So you can explore. You see here, these are all the things. Very good field if you want to explore. I strongly recommend this one to build some entirely new proof of concepts or proposals or prototypes. Okay, we have another 7 minutes. Before jumping into closing part, if any question, I ready to answer. If no questions, I will review what are the things we have discussed since 6 o'clock. So I started with introduction to quantum machine learning. I just explained. I'm keeping a slide for classical machine learning. Then I explained how quantum machine learning is considered as the next big thing. Then I started explaining the fundamental concepts, and then later I stopped with the superposition. I stopped. I did not go to entanglement and all. But anyone want to understand the foundational classes, feel free to connect with me. See, there are multiple training platforms are available. If you are interested, you can learn from them. Then I explained the mathematical foundations for machine learning. I strongly believe that all of you understand these 4 mathematical model. In my humble request is that please inform your students machine learning is not Python programming. Machine learning is mathematical model. After they have to start with a mathematical model. After that, they can implement using Python, Julia, or MATLAB, or Octave, or C, C++, Java, anything. So machine learning is not programming, it is a mathematical modeling. That is the important point. You have to inform your students such that the students come prepared for industry, because we are struggling to train those students who are thinking that machine learning is the Python programming. When we say that we have to implement Julia, oh, Julia, no, we don't know how to implement in Julia. But for production purpose, we need C, C++ or Julia implementation. That's the challenge. So please convey that one. Then we discussed the Venn diagram of QML. Then I started demonstrating the quantum support vector machine, where we learned that we need 4 components like feature map and a QPU interface, then fidelity, then kernel. And these are all created with the various components from Qiskit ecosystem, like Qiskit machine learning, Qiskit algorithms, and Qiskit primitives. From there, we are creating a system for quantum support vector classifier. If you need it and you want to process continuous variable, you can use quantum support vector regressor also. One good thing with the Qiskit machine learning, it will support both classifier as regressor. And there is a one more important quantum machine learning library is called PennyLane. Sorry, I forgot that one to tell. This is very, very important. I strongly recommend all of you to explore this PennyLane.ai. And this one is more stable machine learning library. You should start exploring and learning PennyLane, because PennyLane has a good learning material also. You see documentation, and there is a so PennyLane explore demos. If you go to demos, you will see quantum machine learning, quantum chemistry, quantum computing. See, PennyLane recently came, meaning that around 2021-22, that time only they introduced. That time they have only quantum machine learning, that is to only 4 or 7 demonstrations. But now you can see they have demo for optimization, chemistry, quantum hardware. Let us go to quantum machine learning. Under quantum machine learning, you will see lot of demos, and that covers most of the machine learning concepts. So my personal recommendation, please explore quantum machine learning using Penny Lane. Okay. And they have a good learning platform also. This is called Codebook. In you can start learning Penny Lane in a ordered flow. So please, my strong recommendation is that start learning Penny Lane. Now coming back to the review, then I explained how the quantum neural network are built with the help of rotational gate and entanglement. By repeated rotational gate and entanglement, we can build the hidden layer. Then comes the benefits of QML, then challenges. This one I did not explain, but I kept it the assumption that you will ask, so I'm removing this one. Then the QML versus classical comparison, those things I did not discuss because those are all just in from this PPT you can learn on your own. Then I discussed the quantum encoding, which is essential part to understand. Then PQC versus PQC and VQC. Then how quantum representation or quantum system is represented using a normed complex vector space, which is also called Hilbert space, and how your linear hyperplane is performing non-linear operation for the classifier. But for a neural network, it is a different way, but the same infrastructure is used there. That is what we covered under quantum machine learning. Then I shared some of the books and then YouTube channel. My personal YouTube channel, my preference is 3 blue, 1 brown. Of course, Gilbert Strang book is also a very good one. If you want to buy the paper pack of Gilbert Strang, it will cost 4,000 rupees. But it is worthy investment. You can ask your college to buy that book. And next we covered the quantum inspired algorithm, where I was talking about why we need QLQA, then the principle, superposition, entanglement. These are the only thing are used. Interference is not used. And then we explored quantum inspired evolutionary algorithm and genetic algorithm and quantum inspired PSO, particle swarm optimization. That's it. And then I share the code for the QSVM and the QAEO. For neural network, I did not share, but I showed you a small clip. That code I will share now. Okay. That's all from my side. If nothing else, over to you, madam. Thank you.
So thank you so much for the informative session. And this is the first time the participants are getting the hands-on experience. And really, it was so interesting, and you have pumped us so much of information. I think it's up to the participants to work on that. Whatever you have shared, I think whatever you shared and to work on it itself will take another 6 to 7 months, and exploring will take another 6 months. So, and you're one of the best, and really, we are lucky that you have accepted my invitation to take a session here. I find myself very lucky to have you in all the workshops that I have conducted on quantum till now. Really very much thankful from our management, from our faculty organizers, and from our participants. We extend our heartfelt gratitude for spending a solid 4 hours of time with us. And we wish to be in touch with you in the future also for many more sessions.
My pleasure, madam. Thanks, madam. I'm looking for interns also. So any bright student in your colleges, feel free to connect with me. We are building a strong workforce here. Thank you.
So all of you can connect with sir through LinkedIn, and any internship opportunities for student also you can get connected with sir. For sir is a founder of a company. I hope you're aware of that in sir's introductory note. So if any student requires internship, please do connect with sir through LinkedIn. And the number, if anyone needs, I will share with you all of you in the WhatsApp group. Thank you once again, sir, and have a great day.
Thanks, madam. Bye-bye.
Yes. And to all the participants, please do fill the attendance and the feedback forms that we have shared in the chat box. Please don't forget to fill that. Based on the attendance only, we will be providing the certification. And on the last day, you will have a question answer quiz, which will be based on all the sessions that have been covered in these 6 days of the online course. So goodbye, all of you, and have a
Thank you.
great
Bye-bye.
time. Yeah, thank
Thanks,
you.
madam. Thank you. Bye-bye.